Hey everybody. So let's talk about this cloud render. This was a fun project that I took up recently. And as you can probably get from the title, but it is a cloud render that is deployed into a Kubernetes based environment, whether that be a local Minikube environment or even something like Amazon EKS and AWS. The images that it can render, one example, as we see here, it's pretty much a generic scene template. The interface, as you'll see later, allows you to cast a color to the primary sphere here on the right, but the reflective spheres actually stay the same. So minimal in nature, but it actually pretty much gives you the groundwork for a much more sophisticated cloud render of any type. So let's walk through a little bit about the system, and then we can go ahead and do a little demo to show you it in action. But I've got everything documented in GitHub. So you can see here, it's just under my cloud render repo. I've got a folder for deployments, for the infrastructure that you need to create in AWS, and ultimately the source code. The example I just showed you. This is an MIT license, so I don't know much about licenses, but people can use it. The README and a little GIF showing a demo. But so I've called it the Potato Farm Cloud Render. It's a implementation of a scalable cloud render. And so the idea being that you have three separate, independently scalable components or microservices in the Kubernetes world. But you have a front end, you have a manager or a scheduler that is going to be taking all the incoming jobs that were created from the front end and kind of tracking that in a DynamoDB table. And based on the state of the system, whether it's got too much load or if there's jobs in queue, it will queue up those incoming jobs, or it will pass them to the renderer to begin a render. And naturally, the third component here is the renderer. And this is probably the most, interesting piece here. So it is a ray tracing based renderer. And for anybody that knows rendering or ray tracing or graphics, the ray tracing in one weekend is a awesome series to get you started in this sort of tech and learn the fundamentals of ray tracing. And I've actually been taking up Go a little bit recently, so I actually use Go to implement this ray tracer, and I came across a repo by Hunter Loftus, who also, if we open this up, had gone through the ray tracing in one weekend series and put together a Go implementation of it. So for anybody looking to play around with ray tracing in Go, this is probably a good place to start. Essentially, I used a lot of the same structure, but extended it to use in-memory PNG files, and then integrated it into a web API and set it up to communicate with S3 and AWS to store the files. So the actual architecture we can see here, it may seem like a lot here, but bear with me. It's actually primarily just the three components. You've got the front end. Don't need that. The front end, so it's a React-based front end. Everything is containerized via Docker, and we've got a Kubernetes pod. So this is the lowest level resource can be compared to the container and in a Kubernetes cluster or environment. And so this React build, it's a multi-stage build, and so instead of doing a dev environment with npm start, we actually build it down to an nginx server, and so it's all static assets, and there's a proxy that takes those outgoing backend requests and passes those to the manager. You'll also see here the services. So, sort of the details of Kubernetes are probably out of scope for this, but there are some primary components in Kubernetes that kind of build out an application. You've got your pods, services, ultimately deployments are kind of the high level combination of these things. So when I deploy this, and you can actually see this in the deployments folder. I have a deployment for the front end, which creates the pods and the front end service to manage incoming traffic and communication to other services. I've got a deployment for the manager service and a deployment for the render service. Just the render in general and the manager. So the front end is React based. Manager is a Node app. It's an Express server with the API to kind of manage the incoming requests from the front end, get state from DynamoDB, and pass that back to the user in the browser. And then ultimately pass that information off to the render service to render a job. The AWS components, we've got Cognito, so for your authentication, make sure that a user can access your site. And then the files are all being stored in a Amazon S3 bucket, and then all the job state information is tracked via DynamoDB tables. I've actually tested this in a local Minikube environment, and then I ultimately deployed it into Amazon EKS, and it works the same, both ways. Just slight variations on configurations, but very, very comparable. So if you want to test something out like this in your local system, Minikube will do just fine. But if you have access to a cloud-based environment, it doesn't have to be AWS. It could be Azure or GCP. All those will get the job done. And then we won't talk about it much, but you'll get to see it a little bit when I show the demo. But for your monitoring and logging, we've got the standard EFK stack with Elasticsearch, Fluentd, Kibana, and Grafana and Prometheus. But to kind of show how, so there's kind of a lot of arrows here, but if I was to walk through how a user actually uses this, they'll go to the browser, the client, they query the front end service, which pulls the files for that front end UI, that they can then create a job, pass that job to the manager. It will check state in DynamoDB, make sure that there's not any jobs in queue. If not, cool, we'll go ahead and start it, passes it to the renderer. The renderer will complete its job. When it is done, it will put the file into S3. It will then tell the manager service that, I completed that job. The manager will update the status of that in DynamoDB. And then the front end, you can pull that information, refresh your status, and get that. And ultimately, when you have a complete job, they can press, one of the complete jobs, pull the file from S3 and view it, or download it if they want. So that gives you kind of an overview of the flow of things. Here is just a little GIF of the interface. We'll actually show the demo here, but this gives you an idea of what it might look like. You can see that I've got 3 sliders for RGB just for that primary sphere. You can give it a name and ultimately see if there's any jobs in queue, if there's any active jobs, or what jobs have been completed in the past. The scheduling logic, essentially what it does is it just checks if there's jobs in queue. If there is, put it in the queue. If not, check if there's too many active jobs. Right now I've got kind of like a generic hard-coded value. I think it's something like 4 or 5, but that could be modified to whatever production system you have or scale that you need to maintain. Anyways, if there's too many active jobs, also put it in queue. If not, start the job. And render a job. That goes to the renderer, of course, but when it's done, it communicates that back to the manager that it's finished, checks if there are any jobs in queue. If not, okay, just don't do anything. But otherwise, pull the job from the queue, as we see from here, and then start that job, and the process repeats until the queue is empty or all the incoming jobs are finished. So that is the kind of the manager or the scheduler that we see in that middle component. You've already seen the example render. Future work, yeah, it's very simplistic in nature. The UI is very basic. The system itself is sort of restricted in how complex of a scene. And essentially we're just the standard scene, but a colored sphere here. In the future, it'd be very probably, well, maybe not very straightforward, but fairly straightforward to extend this to get a more complex scene definition, so that you could interact with the positions of spheres, or spheres versus different shapes, and where the camera is and whatnot. It'd also be fun to put a WebGL view kind of preview in the user interface. And then ultimately right now, you can't actually see the progress of a job through the user interface. You have to go through the logs on the back end to kind of get visibility into that. So that would be something that would be nice to have in the future. Before we go in too deep on the code, let's actually show you some of this in practice. So I've got a few things opened up here. I've got the interface that you'll see here in the top left. This is the console for an EC2 instance in my environment that I can run any of my commands to configure my cluster. And this is something, so this is KubeOps view, or Kubernetes operational view. And it's actually a really handy tool because it can tell you or show you the configuration of your cluster. And so you can actually see, how many resources are being consumed at a time, where your pod's being placed, and so forth. So it's actually really useful to get that visual representation. And as it is right now, I've got just one instance of a front end, one instance of the manager, and actually two of the ray tracer. And the only something that was good to call out here is that when you actually launch a deployment, you can specify how many CPUs a certain pod will use, and if you specify that resource, then it will use that to sort of track the state of that particular deployment. And if it needs to do any scaling, and you have scaling configured, then it can actually use that. And so you can see this red line here. This shows you the requested CPU that I've actually provided for my ray tracing job, because the only two that I provided it for were the ray tracer. And if you were to look in the deployment files, you'd see that I have a value set to something like 1.6. Essentially, in this configuration, I'm using just T3 smalls, a fairly small instance type, and they have a capacity of, as you can see here, two CPU units. And so by specifying a value of 1.6, it could probably be something smaller, but still bigger than 1. I actually make it so that when I deploy my renderers, only one renderer will be placed on a node at a given time. And so it just kind of helps in terms of your availability and just distribution of your compute and jobs. So this is useful to kind of see your state. I've also got my logs here down below. If I was to do anything here, we'll see that get updated in this interface. Prometheus, just to be able to see how much CPU is being used per pod. You can see I've been doing some test runs of jobs in the past. You can see where that CPU spikes up. But to kind of show you, it's actually dynamic, the view here. So if I was to delete a deployment, I can see that I've deleted my ray tracer deployment, and you'll actually see the operational view show that there's X's. It's going to be deleting those resources, and eventually they're gone. They're gone from the cluster, and we see that reflected in the view. The same thing applies for when we want to apply any sort of deployment. So I can similarly turn around and deploy something, and it will show you where those pods were created, and then ultimately when we run a job, we can see how much CPU is being used. So let's actually go ahead and start running like a job. So create a file name, specify any given color. I'm kind of a fan of the bluish color, so I'll do that. Schedule it. Give you a queue saying that the job was started. If there were too many in the queue, if there were too many jobs, eventually it would tell you that it was backed up. So we'll see that job is actually active now. Video demo. So when something finishes, we can see the complete jobs and open this list. For example, this is a green one. I can go and open that up, and we'll see that image. Download it, delete it if we need to. But we can also see here down in the logs that we got a job with name video demo, sphere color that what we chose. It's scheduling the job. Says there's no active jobs, and then right now we have a generic size. But so that will begin actually rendering that particular job. As I mentioned before, you can actually see where that job landed, so we can see that there's actually being CPU consumed. If we go into Prometheus, Grafana, we can also see that based on our requests, we're using about 35% of our CPU. And now I actually have the horizontal pod autoscaler configured, and so we can see that at 50%, if it exceeds 50%, I'm going to start, the system will scale. And so at a minimum, it's going to have 2 active pods, which is what that starting configuration was. And I can scale all the way up to 6 if needed. So for the fun of this, let's start throwing jobs at this. Let's just make some generic colors. There's one, maybe job 2. Let's maybe make that more blue. We'll just keep doing this until we eventually hit something in the queue. Job 4. Oh, okay, there we go. So we can see that our system is, saturated in a sense. We've got too many active jobs, and so now we're going to add that to the queue. And so we see there the 4th job has been placed in the queue. And as if we were following it, we'd see all this reflected in the logs. But we'll also, as things start to kick off, see that our CPU usage will start skyrocketing in some places. And so actually we just caught it. So we saw that some new pods were being scaled because our CPU was way up there. So we're seeing here 92%. Obviously that's above 50%. And so now we've gone from 2 replicas to 4. And so it will continue to try to catch up based on the resources that are being consumed or how many jobs have been pushed. But you can sort of see the benefits of this sort of architecture and system in something like Kubernetes in some sort of cloud environment such as AWS. You get easy visibility. You get pretty nice manageability in terms of getting visibility into what's happening, and you can set up your own kind of levers to make sure that it scales automatically to however many jobs are coming in, and it just makes it easier to manage. Rendering is a pretty time consuming, and if you're using the CPU intensive, I know there's more sophisticated GPU based options out there, but CPU is still a viable option. And so we can still see here that the horizontal pod autoscaler has been updating, and CPU utilization is actually still above, but it'll continue to sort of try to match based on the overhead that it's trying to manage. Well, it looks like we actually have some jobs that were being finished. So, so the very initial one, and we can see it there that it's still trying to catch up, so it scheduled even more. If we see the video demo, there's the initial color that we had there. You can go ahead and close it. And actually, you just saw there that because this completed and we had a job in queue, it actually took that job and started it. And so you kind of see the actual representation of how this sort of cycle continues as incoming jobs are being processed and started. So that gives you sort of an overview of the system and how it works in Kubernetes, how you can kind of see the logs as things come through. This is with the Elasticsearch, Kibana, and FluentD, as I described earlier. And then Prometheus and Grafana can give you that sort of visibility at the CPU level, or there's all sorts of sophisticated dashboards you can create. So let's go back into the code, and I guess we can see here that there were some other jobs that we're starting to finish up. Video demo job 1. Yeah, so this will just keep going until the system is complete with all those jobs that we started. Let's go and show a little bit of the actual implementation. So we talked about the system architecture. We've got AWS, we've got Cognito for authentication, all those files in S3. So when I was clicking on those complete jobs, it was pulling those from S3. All that state was being tracked in DynamoDB. And the information was being passed between each of these microservices. And as we saw, I was demonstrating it on the renderer because that's just where the most compute kind of power is needed. But any one of these components can be scaled independently as needed, which is actually really, really powerful. So when we deploy this, let's just show that real fast. I've got some deployment configurations for AWS as well as Minikube. Let's just show AWS for now. We'll have 3 YAML files. Again, if you're interested in the details of Kubernetes, I would encourage you to go, do some reading. Most of Kubernetes is configured via YAML files, so you'll learn to love it. But kubectl, which is the tool used to kind of interact with your clusters or your Kubernetes environments, we can apply all those deployments. So it's pretty generic in terms of the front-end manager. I do call out that this is all communicating with AWS, so you will need to define a configuration in your Kubernetes environment via a secret. Once you have that, those will be deployed just fine, and when they need to communicate with your S3 bucket or with the DynamoDB tables, it will know where to look. I've also called out, I mentioned it just a bit earlier, but when you're deploying the render, I call out that in the AWS environment, I specify how many CPU units, and using that allows you to distribute your nodes evenly across, your pods evenly across your nodes. So once you have, once you've applied all these deployments, you will have a system up and running, and you can start to sort of play around with it. Now, the same stuff applies to a Minikube environment locally, as I outline here. So those are the deployments. I also show you, because there is AWS pieces here, I show you, how to create an EKS cluster. The EKS workshop is a great starting point. There's a section there called Launch using EKS Cuddle, where it shows you step by step how to create a cluster pretty easily. And then most of the deployment, it all follows the same policies. DynamoDB tables. I would call out this caution here. Of course, this is an AWS or this is a public service. So, before you launch anything, just make sure you understand, if you're going to be charged or what are the cost implications of launching those resources. Now, there's a free tier for actually most of the services. So, just take a look at that. And if you're going to do any testing, just be wary of that. And at the end, destroy anything just to prevent any future charges. The tables, I've got 4 tables, one for the job queue, one for active jobs, complete jobs, and then one table that I use is just sort of tracking generic counts of different state of the system. Cognito user pool, identity pool for login, and then the S3 bucket for actually holding the files. Now this uses a library called Amplify, and so it's actually an amazing library to integrate into your applications and communicate with various different AWS services. So go ahead and check that out if you haven't before. So we talked about deployments, the AWS side. Let's actually talk about the code. So we've got the front end. We've got some Nginx configuration. This is because we're doing a multi-stage Docker build, and so ultimately we're having an Nginx server. We pass it the default configuration with the endpoints that we're going to be calling, so that it can actually proxy that to the backend. All these I'm using makefiles in terms of just building. So I will say, I'm on a Mac system. There might be some small tweaks if you need to do this on a Windows machine, but most of the same principles will apply. The front end, as I was calling out, you use Cognito and Amplify, so you need to initialize that with your identity pool, the web client ID, your user pool. Make it with Docker, because you're actually making a Docker image, pushing that to Docker Hub, and then ultimately that's what the deployments are pulling from when you put this into your Kubernetes environment. The React application, if you haven't tried it out, I use Create React App for almost any React application that I do. So if you want a good starting point for React applications, I would highly recommend starting with Create React App. Same demo that you've seen. Workflows. Yeah, as I showed, you can create jobs, you can get the status of those jobs, you can delete completed jobs, and ultimately view them. So now the manager. So this is where the scheduling is taking place, as I talked about before. Same steps. Make your Docker image. I can show a Docker image. If you need to get up to speed on Docker, there's plenty of resources on YouTube, on their site, and in books and all over the place. But you're always going to want to containerize your application before you put it into your Kubernetes environment. It's just kind of a requirement. There's different ways to do that, but Docker is one such way. And so you have a Docker file. It defines a configuration, sort of a layered approach in terms of base images, and then you're passing your files, running any commands to get those files onto that system, installing, and ultimately it kind of gives you an entry point or a command to start that container. But the manager itself, we've got scheduling logic, as I described before, just checks the queue, checks active jobs, and kind of manages that cycle. The API, we've got a schedule job API. I've outlined the types of requests. So we've got posts, different information. Right now it's very simplistic. So we've got name, RGB, and write mode. So this write mode I use for local testing as well as configuring my my cloud-based implementation. So if I set that to say 2, then it's just going to write it to S3. But if I'm testing it locally, I can set it to 1, and it'll write me a local file on my file system. Report finished job. So when a job completes, this is what the renderer reports to, saying, this is the project, or sorry, this is the job name that I finished. If the user deletes something, it will remove it from the completed, and ultimately status, which gets all the job state. I guess I can show some of the code as well. It's using Express. Feel free to Google Express and take a look at some example applications, but it's a pretty good tool for making web servers with Node.js. So we've got generic get for just me testing, just saying that I'm operational, but you can sort of review some of these files at your own leisure to get an understanding of what the system is doing. But let's talk about the renderer. So as I mentioned, this was started with a Go implementation by Hunter Loftus. You can go to his repo if you want to play around with ray tracing in Go. If you want to learn, the fundamentals and how this stuff is actually working, you can go to Ray Tracing in One Weekend. It's a great place to start and learn. I wrapped it with a web API, as we saw, and the traditional implementation actually writes files, in generic ASCII to a PPM file, but that's kind of a lot of overhead. So for something like a cloud-based rendering system, it's kind of better to work in memory, and PNG files are the sort of a standard. So I just modified it to write those into that format. Same build steps apply, and the example render. The API, we don't actually really use this when it's actually deployed in the cloud, but this was for some of my local testing when I was building it on my own system. But primarily the start job is what it's going to be called. So when a job is scheduled and ready to go, it'll pass, the manager passes that information to this endpoint, gets the name, the colors of the sphere, and then the write mode. But I mean, that's essentially, most of the system. Gives you a pretty good overview of what's happening here. This is just one implementation of such a system. These type of things are as much an art as they are science. So, there's a lot of creativity that goes into these things. I'm sure my implementation is not the most optimal. It's just one such way. So I would encourage you, if you ever do these sort of projects, or maybe you want to extend this, find your own ways to optimize these things. But as I mentioned, this is sort of a foundational approach. It kind of demonstrates how, a cool technology such as rendering and ray tracing can be applied in a containerized and cloud-based environment, and the power that allows you. So hope you enjoyed that. Feel free to play around with the code, or if you have any questions, feel free to reach out. And with that, have a good one. All right.